Hello students, let us continue the discussion on units and measurements. So in the last session, we were discussing about one of the application of dimensional analysis, isn't it? In the first place, we got to know what are dimensions. What are dimensions? Dimensions are the powers to which the base quantities are raised to represent the given quantity. For example, the dimension of length is capital L raised to 1. And similarly, the dimension of force is m l t minus 1, t minus 2. So m1 l1 t minus 2. We use the lmt form in some reference, and in some reference we make use of mlt. Okay, that's not a problem, but it's all about length, mass and time. Normally we take these three quantities and express the powers to get represent the given quantity, like force, work, momentum, etc., etc. And now we shall continue our discussion for the second application of dimensional analysis. The first application of dimensional analysis is to uh, convert from one system of unit to the other system of unit, isn't it? Yes, in the last session we successfully converted Newton to Dyne and Joule to ergs. Those are the two standard conversions that we have in our syllabus. We can also do conversions for other quantities also. And in this session, we are going to look into the second application or second use of dimensional analysis. The second use or application of dimensional analysis is to check the dimensional consistency which is also considered, or in other words we also say this as to check the correctness. Okay, instead of dimensional consistency we can also say to check the correctness of given equation. What do you mean by this? So we can check the correctness, whether the given equation is correct or not. Yes, that can be checked using dimensional analysis. Let us take an equation. Okay, say there are many equations that we find in the syllabus, but sometimes the equations can be wrong. If when you are writing them down, can become wrong, or the chances are also there that one can give you the wrong equation during discussions and all. But there is a way to check whether the equation is dimensionally consistent or not. In other words, we can check whether the equation is imperfect or wrong. Okay, I'll give you the example, we'll get to know. See, there is one equation which is v is equal to u plus at. I hope you are familiar with this equation. This is the equation which belongs to equations of motion, very easy equation, where v is final velocity, u is initial velocity, a is acceleration, t is the time taken. Now, if this equation needs to be correct, wants to be correct, then the dimension of v, u and at, all of this must be same. Okay, in the first place, what is the dimension of v? V means velocity. The dimension of velocity is simple, it is L1 t minus 1. That's it. Clear? So it's done. Now coming to this part, the RHS part, what is the dimension of u? Dimension of u. What is u? U is again velocity and its dimension is L1 t minus 1 again. So that's it. So this much equation is so far dimensionally consistent. And moving ahead, see, even this at must also have the same dimension. Okay, when it comes to dimensional analysis, one should understand that positive or addition subtraction and equals, all of them mean the same. Okay, see, this part will have the same unit, this part will also have the same unit and dimension, even this part will also have the same unit and dimension. So when it comes to dimensional analysis and units, equals, addition and subtraction, they all mean the same, okay, in dimensional analysis. So positive in the play, even if we have something like negative sign, even that it should also the other part, which means even if the equation is u minus at, even in that situation, this and this term, okay, all of them must be must have the same dimension and same unit. Okay, so now this is not positive, we are not going to add dimensions, it's all about comparing dimensions of each term. Okay, and when I say each term, addition of terms and subtraction of terms and equals of terms are meant to be same, is equal to. So what is dimension of at together? Okay, at together, dimension of a is L1 t minus 2, right? Isn't it? We have discussed about it. What is dimension of t? What is t in basically? T is time taken, right? So dimension of small t is simply capital T. That's it, isn't it? So in the next step, we shall see that, okay, dimension of v L1 t minus 1, dimension of u L1 t minus 1 again, so far consistent. At together is L1. See, when this T1 is multiplied with T minus 2, it becomes T minus 2 plus 1, isn't it? And in the next step, we have L1 T minus 1 is dimensionally consistent with L1 T minus 1 of U and is dimensionally consistent with L1 T minus 1 of AT. So, using this dimensional analysis, I have concluded that this equation is dimensionally consistent. Okay, dimensionally consistent. So, what is the use of this? What is the use of checking the dimensional consistency? See, this is like a basic basic checking of the equation, or a basic validating of the equation, which means if the equation fails this dimensional consistency, then the equation is wrong, it's completely wrong, it can never be right. Okay, if the equation fails dimensional consistency, then it is wrong. But if the equation proves the dimensional consistency, passes the dimensional consistency, then it can be right or wrong. It should be verified again, because see, in the place of simply u, it can be 2u, and in the place of at, it can be half at. Like that, it can be any constants can come, okay, any numbers can come in here, and they are not mentioned. So those numbers are to be verified using the actual experiments, then only we can say this equation is perfect. But what is the use of dimensional consistency? Dimensional consistency will give us the basic idea that whether the equation is wrong or it can be checked again. If the equation fails dimensional consistency, it is said to be wrong. If it passes, or if it verifies the dimensional consistency, then we have to check it again for the further validation. Clear? So this is one equation for which we check the dimensional consistency. Moving ahead, let me take one more equation of this kind, okay, and check the dimension consistency. Say I have an equation, say S is equal to ut plus half at, okay, ut plus half at. If I have such equation, S is equal to ut plus half at, then now I need to check whether this equation is dimensionally consistent or not. Okay, let us check it. Now, as I've informed you that all of these terms, S, ut, half at, okay, see, what is the mathematical operation between ut and half at? It is addition, right? So we don't bother whether it is addition or subtraction. It's only about the terms adding together or subtracting together must have the same dimension and same unit. Keep that in mind. Okay, the terms which are adding up with each other, subtracting with each other, and equating with each other, okay, and equating with each other must have the same dimension and unit. So now let us check all these terms has the same dimension or not. Dimension of S. What is S? S is displacement. Displacement is simply length. So dimension of S is simply L1 because it is simply length. Then what is the dimension of UT? UT together I have to take. Dimension of U is L1 T minus 1 and dimension of small t is T. What is T actually? T is time. That's it. So it is T plus half is a constant. We don't need to bother about constant, and since we have considered the dimensions, that half shall be replaced by equals because they must be dimensionally consistent, whether it is subtraction or addition or equating. So it is L1 T minus 1 for U, T1 plus 1 for small t, then no value for half. Half is a dimensionless constant, it's just a number. Then I have A. What is this A? Just a minute. What is this A? A is acceleration, right? So dimension of acceleration, okay, is L1 t minus 2. And what is this small t? Small t is again time. So it is T1. Now let us check for the validity or the equating property. So it is L1 for length or displacement, and here comes T1 into the equation and becomes L1 T of minus 1 plus 1. Okay, this plus 1 came here, following, is equal to, and AT is L1 T minus 2. This plus 1 came here, so T minus 2 plus 1. And finally we have L1 is equal to minus 1 plus 1 is 0. Anything to the power of 0 is 1. So this term goes away. Which term? The term of t in the second one, ut. So this t goes away and we are left with L1. So far equation is consistent dimensionally. Now comes the last part of the equation, and here I have L1 left and t raised to minus 2 plus 1. What is minus 2 plus 1? Minus 2 plus 1 is minus 1, isn't it? Minus 2 plus 1 is minus 1. So now, yes, L1 is equal to L1, but is not equal to L1 t minus 1, isn't it? So the last term of the equation is not proving the dimensional consistency. It is not valid for dimensional consistency. So what I can conclude now from this is, since it is not equal, even if a single term does not prove the consistency dimensionally, then we can say that the given equation is dimensionally inconsistent and hence it is wrong. Okay, so I can now confidently say that this equation is wrong. Okay, confidently. But what I can say with this equation is, I can now say this equation is dimensionally consistent, the first one, but I cannot say it is right equation because it has to pass the practical values also. But this one, I don't need to check for practical practical situation using practical values because it fails in the first step itself. The first step is checking the dimensional consistency. Since this equation fails the dimensional consistency, so I can conclude it as such. Okay, therefore the given equation is dimensionally inconsistent. Therefore the given equation is dimensionally inconsistent and hence wrong. That's it. Okay, this is how you should conclude. But how do you conclude this? We conclude this by saying the given equation is dimensionally consistent. Okay, that is how we write and conclude the first equation. This is wrong, okay, because it is dimensionally inconsistent. Clear with everything? This is how we make use of second application. Okay, let me give you one more example of this kind and go ahead for the next. Okay, let us take one more example and check the dimensional consistency of the equation. So let me take a very easy example which you all know, something like the uh, area of a circle, okay, or let me take volume of a cube, okay, or volume of a cylinder, let me take, okay, because I want to involve so many factors, that's why. Okay, volume of cube is given by 4 by 3, okay, sorry, we have so many volumes to which we can include, okay. One of that is volume of cube 4 by 3 pi r cube, okay, and volume of cylinder, we have one more formula, which is pi r squared h, okay. You pro, okay, you check it, these are the homeworks for you, okay. You check the dimensional consistency of this equation and this equation, okay. You'll find that what to do with this pi, okay. Anyhow 4 by 3 is just a number, that this number has got no dimension, so no dimension of 4 by 3, that's fine. What about pi? What is this pi? Pi is again a simple number, no need to worry about the dimension of pi, because pi does not have any dimension in it, okay. So pi is a dimensionless constant, okay. What is pi? Pi is just a number, it can also be taken as dimensionless constant, okay. So there are so many factors which come under dimensions like this, which are dimensionless constants, and the constants with dimension. Yes, we do have so many constants with dimension, and if we have such a such constants or such constants in the equation, for example, I'll give you like the example expression or formula of gravitational force, which you might know, F is equal to G m1 m2 by r squared, right? So in this expression you can see both m1 m2 r, all of these quantities has their dimensions, mass and length. Even force also has its dimensions. So but when you check G, what is G? G is the universal gravitational constant, isn't it? Here G is not a dimensionless constant, this is a constant with dimension. So if you are asked to write the example for a constant with dimension, then universal gravitational constant R G is the example. Clear with this? Because this G has its dimensions. Okay, you can work for the dimension of G. How do you get that dimension of G? It can be obtained by using the equation of G. So if you send all the other terms here, equation of G becomes f r squared by m1 m2. You check that, put the dimension of f here, put the dimension of L2 and m2 in the denominator, put them together, you'll get the dimension of G, okay. So it's again another work for you to get the dimension of G, okay. What is G? G is the universal gravitational constant. What kind of constant it is? It's a constant with dimension. And what about this pi? Pi is also a constant, but is this time this pi is a constant without any dimension, okay. So we can say pi is a constant without dimension, G is a constant with dimension, okay. Why am I telling this here? Because when you check the dimensional consistency, you should have the idea about what kind of constants you have, okay. If the constants that you have also has the dimension, you should consider the dimension of those constants also, then only you can get the clear idea about dimensional analysis, okay. You do the dimensional analysis for with these two and check the dimensional consistency, okay, fine. So now let us look at the third application of dimensional analysis. The third application of dimensional analysis is dimensional analysis can be used to deduce, okay, to deduce or derive, okay, deduce or derive, both are fine, you can write either deduce or derive, relationship between various or between different physical quantities. Yeah, this is not the absolute perfect method, but yes, it can be used in certain situations. We'll see what kind of situations uh, in which we can make use of this application of dimensional analysis. I'll explain it with example. Okay, basically it's about we can connect how one factor is dependent on other factor. Okay, that's how we can connect two quantities. Okay, right. There is let me take the example of time period of simple pendulum. Okay, we have seen this experiment. The simple pendulum is as follows. This is the support and this is a thread of length L to which a bob of mass m is connected, and this bob, the simple pendulum, is pulled downwards by gravitational force, and the acceleration due to gravity is small g. Following? So now I think there are many factors on which the time period of simple pendulum depend on. You all know that time period is the time taken for one oscillation. I've done the experiment in the bridge course. So now I think time period, okay, time period of oscillation is dependent on, there are so many factors that I can choose, but I now see the factors which I can vary, I can change. I can change the length. So I think it depends on length. But I don't know how it is dependent. It can be dependent on L to the power of 1, L to the power of 2, which means L squared. It can be dependent on root L. It can be dependent on 1 by L. I don't know how it is dependent, but what I know is yes, it is dependent on L. Okay, it can be. I think so. So what I take is L to the power of small a. Okay. Finally, we'll get what this a b, this a small a. But now what I have considered is let t is dependent on L in such a way that L raised to a decides the value of t. Okay. Then I think that it can also be dependent on mass of the bob. So I'll take one more factor m, mass of the bob, to the power of b, small b. So this is one more factor. M is the mass of the bob, which I think the time period of simple pendulum might be dependent on. And I take this factor m to the power of b. And I think again these are the possible variables. Okay, the factors which can vary in the experiment. So I also think that it can also be dependent on g. So I'll take g to the power of some c. Okay, I think these are the factors. How and which are these factors which decides the value of time period. Okay, so now my intention would be to get the values of a b c, and hence I can get the relation, how relation of how this t is dependent on L, M and G. Okay, right, let us start dimensional analysis. Let us balance the dimensions on both the sides. Okay, so dimension of t, what is t? T is time period, time taken for one oscillation, whatever it is, finally it is time. Okay, so the dimension of t is simply capital T, T1. Okay, that's it. And in the RHS we have L raised to a, M raised to b, G raised to c. What is L here? L is the length of the pendulum. It is length, that's it. So it is L1 raised to a. Okay, what is M? M is mass of the bob, mass, very simple. So it is capital M raised to b, and we have G. What is G? G is acceleration due to gravity. Acceleration due to gravity. So finally, it's acceleration, nothing else. Okay, and this acceleration is due to gravity. We don't bother. The acceleration is due to gravity or due to centripetal phenomena. We don't bother about it. Finally, it is acceleration. So this G will have the same unit and dimension of acceleration. So unit and the dimension of acceleration, you all know that it is L1 t minus 2, isn't it? L1 t minus 2 is the unit of dimension of acceleration, and L1 t minus 2 raised to c. Okay, we are just trying to balance the powers on both the sides, and instead of L1 I can put them, because since I have LMT all of them in the RHS, I also want to introduce all of them LMT in the LHS. Okay, so for that I can write this as L raised to 0, because there is no L term here, but I can write it as L raised to 0, that is simply 1. I can vanish it afterwards, and M raised to 0, M0, and along with that I can also put that as T1. Okay, L0, M0, T1. So this is how I can write simply T1 as. This is also the right way. Okay, this is the short way, this is the complete way of writing it. And now comes the RHS part. See, L1 to the power of A, L raised to L1 to the power of A, it is going to be LA. And then comes M raised to B. Okay, let me put them in different brackets. And the third one, so it is L raised to 1 to the power of C. So it is L raised to C and T raised to minus 2C. Okay, it's product of 2, no? So that's how it is, minus 2C. And now once again, L0, M0, T1, and in the RHS, see, I here have L raised to A, and here I have L raised to C, LC. Okay, so, and when they are put together, it's going to be L raised to A plus C, right? A plus C, and M raised to B, right? M raised to B, and finally I have T raised to minus 2C. Following? Okay, now what do we do? How do we get the expression? What we actually need is the values of A, B, C. If we get the values of A, B, C, we'll get the connection, or we'll get the formula how T is dependent on LMG. Okay, so let us compare the powers on both the sides. What do we have here? When it comes to length, here in the LHS we have 0, and here in the RHS we have A plus C. So comparing them, it's going to be A plus C is equal to 0. And here we have M raised to 0, and here we have M raised to B. So comparing them, B is equal to 0 directly. So we have obtained the value of B directly. And then moving ahead, here I have 1, okay, and here I have minus 2C, which means comparing the powers of T, I get minus 2C is equal to 1. These are the three equations that I get by comparing the powers of similar terms, similar dimensions on both the sides. So let me solve them. Anyhow, B is equal to 0, we have directly obtained the value. And here, since minus 2C is equal to 1, I get C is equal to, see, negative sign goes that side, 2 goes to the denominator, minus half. I now have two values. One is B, which is directly obtained, is equal to 0, and the other is C, which is minus half. And then since C is minus half, A plus C should be 0. So A minus half should be 0, which means A should be plus half, right? A should be plus half, which can be simply put as half. So these are the three values of A, B, C that we have here. Okay, so that's it. We now have the values of A, B, and C, and hence if I put all these values of A, B, C into the actual consideration, I can get the dependence of T on LMG. Okay, how does it look like? So now a T is proportional to L raised to A. What is A? A is half. So L raised to half. And I have M raised to B, or M to the power of B. M to the power of B, B is 0. So M to the power of 0 it is. And here I have G raised to C. Okay, what is C? C is minus half. So it is G to the power of minus half. So M to the power of 0, anything to the power of 0 is 1. So the middle term vanishes. I'll be simply left with T raised to T proportional to L to the power of half. See, I can bring this G to the power of minus half to the denominator, and hence it becomes G to the power of half. Isn't it? since it is minus half, the power is minus half in the numerator, it becomes plus half in the denominator. Now you have, what is something to the power of half? When we have something to the power of half, it is actually the square root. So keeping them together, t is now proportional to under root of L by G. Okay, so t is directly proportional to under root of L by G. This is the dependence of t on L and G. And this also concludes that the time period is not dependent on mass, isn't it? Because the term mass vanishes, it becomes zero using dimensional analysis. So here we need to remove the proportionality, and in order to remove the proportionality, I need to introduce the constant. The constant can be introduced by conducting the experiments. Okay, so now I have the proportionality. If I conduct experiments, I can get the value of constant which has to be introduced. So then after introducing the constant that I'm going to introduce here is going to be 2 pi. Okay, and this constant can be obtained after experiments. That's fine. So now t is equal to 2 pi, which is the constant, dimensionless constant, into under root of L by G. Okay, so this is the expression of t expressed in terms of length of the pendulum and acceleration due to gravity. Final expression is t is equal to 2 pi root of L by G. Understood? This is how we can deduce or derive the relationship between different physical quantities. Now you see which are the different physical quantities that we connected. Different physical quantities that we connected are time period, length, and acceleration due to gravity. And the phenomena here we are observing is a simple pendulum. Okay, so this is about the third application and the final application, or the use of dimensional analysis. So now these are the applications, the three applications, which means the uses of dimensional analysis. Moving ahead, we also have few limitations. Okay, limitations means the defects or the boundary, okay, after which the dimensional analysis cannot be used. Okay, so let us see which are the, or what are the limitations of dimensional analysis. Limitations of dimensional analysis. Okay, first limitation is while checking for the correctness of the equation. Okay, the second use that we used, that the second application that we discussed, involves checking the correctness or checking the dimensional consistency. As the name itself says, we are checking the dimensional consistency. We cannot check the complete correctness of the equation using dimensional analysis. So that is the first limitation. What it can't do, what dimensional analysis can't do, is discussed here as limitations. So first limitation is only dimensional consistency. Only dimensional consistency can be checked, but not the complete correctness. Not the complete correctness of the equation, isn't it? We have discussed about it. Because if you have the standard expression is v is equal to u plus at. I'll take the simple example. Or let me take one more, like the expression of kinetic energy is k is equal to half mv squared. So instead of half mv squared, if we have k is equal to simply mv squared, k is equal to mv squared, even then the equation is dimensionally consistent, but it's actually a wrong equation, isn't it? So that's the limitation of dimensional analysis. It can only check the dimensional consistency but not the complete correctness of the equation. So that's the first limitation. Moving ahead, the second limitation is about deducing the deriving the relation between different physical quantities. So the value of constant, just before this discussion we derived the expression for t, isn't it? The dimensional analysis came till t proportional to root of L by G, but the perfect expression cannot be obtained because the value of this the value of the constant that comes in the equation cannot be obtained, cannot be derived using dimensional analysis. Okay, so the value of constant, in the expression, the value of constant in the expression cannot be obtained, using dimensional analysis, isn't it? So that is about second use or second application. Second limitation. Okay, so this we can't do, isn't it? The value of 2 pi that we introduced in the last example, t is equal to 2 pi root of L by G, that cannot be done. The value cannot be obtained using dimensional analysis. I've told you it can only be done using practical situation or practical experiments. But using dimensional analysis, we can go till t is proportional to root of L by G. That's it. Okay, so that's the second limitation of dimensional analysis. And now moving ahead, the third limitation of dimensional analysis is the equation involving more than equation involving more than one term is also fine, or equation involving two or more terms. So the third limitation is the equation involving two or more terms cannot be derived using dimensional analysis. As an example, the equation v is equal to u plus at. Okay, since these are the easy expressions, I'll be considering them again and again, but you'll find a lot of other examples in the next coming classes. That's fine. So v is equal to u plus at involves two terms, u and at together. So this expression cannot be derived using dimensional analysis, because we do know that v is dependent on u, v is also dependent on a, v is also dependent on t. But if we go according to dimensional analysis, we cannot derive this expression because it involves more than one term. It actually involves two terms. So this kind of expressions involving two or more terms cannot be derived using dimensional analysis. And the last limitation is the equations involving trigonometric functions. The equations involving trigonometric functions, trigonometric, logarithmic functions, and even the exponentials. And exponentials cannot be derived. This is one more limitation of dimensional analysis. We cannot derive the expressions involving trigonometric functions. Which are the trigonometric functions? Like sine theta, cos theta, all those other trigonometric functions. We cannot derive the equations involving logarithmic functions. If we have log value, then we cannot derive that kind of equation. If we have the equation involving exponential means something to the power of the variable. Okay, we get to know a lot of other examples, lot of examples in the class, but that's about it. We cannot actually derive it if the equation involves trigonometric functions, logarithmic functions, and exponents. Exponents means, you know, that to the power of some variable. If the variable is present in the power of certain other variable or a constant, we cannot actually derive that kind of expression using dimensional analysis. So these are the limitations of dimension analysis. And now finally we shall look at a few examples of different quantities or different kind of values. Okay, so first I have a few examples. Okay, examples, these are all examples that I'm taking now. If I am asked about, give me an example for dimension less quantity. Okay, dimensionless quantity. Okay, uh, so I can make a table. Okay, both dimensionless and unitless. Some of the quantities are both dimensionless and unitless, and some of the quantities are uh, only dimensionless, but they do have units. Let me give you the example. So if you are asked to get the dimensionless quantity, then one of the example is plane angle. Plane angle and solid angle are the examples. Plane angle and solid angle are the examples for dimensionless quantities. And there are no quantities without unit. Okay, quantities are physical quantities which we can measure. Whenever you measure, you will have certain unit associated with, right? So dimensionless quantity, example for dimensionless quantity is plane angle, solid angle. Next, the example that you can be asked is dimensionless constant. Okay, dimensionless constant. So dimensionless constants, we have so many dimensionless constants. Any number you write, half, pi, was it like 1, and you can get so many other examples. Okay, which are etc., which are dimensionless constants. You have the formula, area A is equal to pi r squared, where pi is dimensionless, r is dimension, the quantity with dimension. It's a quantity, r is a quantity, pi is a constant, and it does not have any dimension. And if you are asked to give the example for constant with dimension, constant with dimension, then the example is as follows. I've told you about capital G, universal gravitational constant. Okay, you should write the complete form. Universal gravitational constant, capital G, is an example for constant. It's a constant, not the variable. It is fixed with dimension. Okay, this G has dimensions. And you take capital R, universal gas constant. This universal gas constant also has dimensions. And you take h, small h, Planck's constant, which is called Planck's constant. Even Planck's constant also has dimensions. Okay, so these are the examples. And one special case I'll take. If you are asked to get the something like a unitless or okay, these are the examples for unitless and dimensionless. Okay, unitless and dimensionless constants are half, pi, 1, any value which any simple constant is, are these half, pi, 1, etc., are all dimension, both unitless and dimensionless constants. Okay, and if you are asked to get quantities or the units, okay, units with dimensions, or units without dimension, units without dimension. So now we need units, but that unit should not have any dimension. See, when I say units with dimension, all the units that we know, meter per second, Newton, joule, and all of them are valid, and we can get the we can write that all those units has dimensions. But if you are asked to write the units without dimension, see, these are the quantities without dimension, and their units are the units without dimension. That's it. So what is the unit of plane angle? Unit of plane angle is radian. So radian, and unit of solid angle is steradian. Radian and steradian are the units which do not have dimensions. Okay, you have to keep at least one example from each situation, each case in mind, and they're asked in 1 mark. Okay, good. Thank you.